I welcome you all in this presentation related with the subject materials processing fundamentals and practical. And we are talking about the powder metallurgy. In this particular presentation, I will be focusing on the various characteristics related with the powders which are used in the powder metallurgy and how the powder particle characteristics affect the powder metallurgy. Okay. So, as far as the various characteristics of the powder particle is concerned, the size, shape and distribution, then surface roughness of the powder particle, surface impurities, surface area to volume ratio, that is known as A by V ratio, especially in powders, surface impurities like presence of oxides, oil, moisture or anything like that, surface roughness in terms of the A, size say in terms of the either or micrometer, or the shape that is quantified in terms of the aspect ratio, and distribution, what is the proportion of the powders of different sizes. So, like say the powders greater than 50 micrometer, 30%, okay, powders between the 50 to 20 micrometer, say 50%, and 20% less than 20 micrometers. So, this is how we can say the coarse particles is of say 30%, and in the moderate size or medium size powder particles of 50%, and the small size particles are of say 20%. So, this is about the distribution. What is the proportion of the different particles of the different size ranges? Okay. Then the surface roughness. Then packing behavior. Packing behavior, there are two terms related with this. One is the density, that is called true density also. There is a normal density. It is about the weight of the material for a given volume without porosity. But when the weight of volume of the material in a given volume with porosity is considered, this is termed as the bulk density. This is also known as apparent density. Okay. So, the apparent density and the true density, these are the some of the important characteristics related to the powders. We will also try to see that how these characteristics can be related with the different stages or steps of the powder metallurgy. Okay. So, the powder shape, the powders can be of like a spherical shape or very irregular shape, needle shape or dendritic shape like this. So, how to quantify? Each powder will be offering the different kind of the flow characteristics. Okay. So, to quantify the shape, we use one parameter that is called aspect ratio. Okay. So, the ratio of the long dimensions divided by the short dimensions. Okay. So, the length to width ratio is indicates the aspect ratio. For circular shape or spherical shape powders, this length to width ratio is almost equal to 1, while that for the needler shape it is like say 4 to 5 also, or it can be 8 also, depending upon the kind of the dimensions. If it is a regular shape, then it may be like say 1.5, 2 or so. Okay. So, the metal powders are produced in variety of shapes: spherical, plate-like, flaky, dendritic and irregular shape. Simple measure of the shape is the aspect ratio, which is the ratio of maximum to the minimum dimensions of the powder particle. Okay. So, as I said, spherical shape powders show the aspect ratio equal to 1, otherwise it can be greater like say 2, 4 or 6 as per the shape of the powders which are being produced. Like the flaky powders may be of the longer or higher aspect ratio. Okay. Shape of the powders affect the flowability, apparent density and compactability. Okay. Compactability. Compactability means how easily powder can be compacted during the compaction stage, how easily powder can be filled in the mold cavity, that indicates flowability. And apparent density for a given volume of the powders in the mold cavity, what is the weight. So, weight and the volume V, this gives with the porosity without compaction, this gives us the apparent density. So, when the shape is the regular, then the voids and the gaps between the powder particles will be more, and that will be leading to the reduced apparent density. Okay, when the powder particles are of the irregular shape, dendritic shape, then the flowability will be very less because of the higher interparticle friction. Okay, but if we have the spherical powder particles, then the interparticle friction will be less, flowability will be better. Okay, and the upper density will be less, so compactability will also be better. Okay, so the powder particle shape affects the flowability, upper density and compactability. Spherical shape powders offer the better flowability, lower upper density as compared to those having the higher aspect ratio like flake and plate like appearances. If the shape is flake and the flake or plate like appearance, or the shape is of the powders is flaky or the plate like, then it will require longer stroke. Okay, as compared to the one which is will be needed for the spherical shape. Why? Because the gap between the powder particles in case of the irregular shape powders is much more, and therefore for compaction purpose it requires the longer stroke. Okay, the size and size range. So how the powder particle size is quantified? So we use the different sheaves of the different sizes. Okay, like this. So the sheaves will be having the openings of the different sizes as per the number of the sheep. Okay, it is like this, and this will be used for the grading of the powders. So in 1 inch 1 inch linear distance, how many openings are there, that indicates the sieve size. Okay, so powders are graded using the sieves of different sizes. Say 4 means the 4 openings in 1 inch, or 100 sieve size means the 100 openings in 1 inch. So obviously these will be very small as compared to the powders that will be obtained through the sieve of number 4. Okay, because it will be having in 1 inch, it will be having just 4 number of the openings that will be obtained after the grading of the powders. So these numbers indicates the number of openings per linear range. Okay, higher the mesh count, smaller the powder particles that will be obtained after grading using that particular shape. Therefore, if we use the powders of one size, then the chances of having the large gap between the powder particles will be more as compared to the case when we use the powder particles of the different sizes, few coarse, few fine, few small, few big, few medium, like this. So if we are using the powders of the different sizes, then the voids and the porosity without compaction will be less, okay, as compared to the case when we use the one size powder particles. Therefore, to reduce the interparticle porosity, to reduce the voids between the powder particles without compaction, it is important that the powders of the different sizes are used. Okay, so large size powders reduce the flowability and they also reduce the apparent density. Okay, but when we use the powders of the different sizes, the flowability is improved and the apparent density is enhanced. We can use the powders of very small size, but that will increase the cost of the product. So it is not economically justified. So powder mixtures of a size range is used in the different proportions, because only if you use the only small size, then it will increase the cost of product significantly. For example, 70% of the 200 sieve size powders, 20% of 325 sieve size and 10% of the 400 sieve size. So this is the coarsest one, then little smaller size and further smaller size in the smaller quantity. This will increase the apparent density because the gap between the coarse particles will be filled in the medium or small size particles. Okay, that in turn will help in reducing the pores between the powder particles. So here we can understand what is the sieve number and meaning with regard to the opening size. So when say the sieve number is 4, the opening size is 4.75 mm. When sieve number is 30, opening size is say 0.6 mm, that is 60 micrometer. When sieve size is 100, the say our the sieve size, the opening is 0.15 micrometer. okay, and when it is 200, then it is 0.075 mm, and when it is 400, then it is 0.038 mm. So, the sieve number, higher the sieve number, okay, sieve number is high, the smaller is the size of the powder that will be obtained. So, what we do, the grading of the powder is done using the sieves of the different sizes. So, we have the powders of the different sizes, then these are mixed in the suitable proportions in order to reduce the interparticle gap and increase the apparent density. Okay, the surface roughness. If the surface is rough, like this surface is rough, then it will the interparticle friction, this will be high. The friction between the particles, interparticle friction will be high, and that will high friction will reduce the flowability. Okay, this is one. And the second one, it will increase the force required for compaction, because if the particles are smooth, they will settle down easily and they will get compacted easily. But if the surfaces are rough, then it will increase the force required for compaction. So, here smooth surfaces improve the flowability and reduce the compaction. If they are not smooth, then the flowability is reduced and force requirement is enhanced. Therefore, powders produced by atomization method offers a better flowability as compared to those produced by the reduction and electrolysis method, because the reduction and electrolysis method produces the particles of the irregular shape with the rough surfaces, higher Ra, that reduces the flowability and also it reduces the ease of compaction. Okay. So, now we will see that how to quantify the ease of compaction, like it is about the force required for compacting with the desired density of the briquette or the product which is being made. Surface impurities, like say this is the powder particle. Okay. If the powder particles are having the irregularities at the surface, impurities at the surface in form of the oxides or other kind of impurities, then during the sintering, the diffusion across the powder particle will be taking place for developing the metallurgical bond. You see, during the compaction, the weak shape component is obtained through the mechanical interlocking facilitated by the plastic deformation of the powder particles. So, in order to increase the strength, it is important that the metallurgical bond between the powder particle is created, and that is done by heating the component after compaction to the high temperature, so that the diffusion across the interface can take place, and that will be possible only if the contact between the powder particle is direct between the metal to metal. But if there are impurities like this at the interface, then the diffusion will be hindered, and these impurities may be of very small in terms of the thickness, like say 10 to 30 micrometer. So, if the diffusion is resisted, then metallurgical bonding process will be slowed, okay, or it will be resulting in the product with the significant impurities as well as significant proportion of the voids and the porosity in the powder metallurgy product due to the reduced diffusion. Okay. So, impurities in form of oxides and lubricant at the surface reduces the metal to metal contact, and that adversely affects the diffusion as well as the metallurgical bonding during the sintering. Therefore, these affect the strength and ductility, because the desired strength and ductility is achieved through the metallurgical bonding. If the impurity is present at the surface is not helping in that, then our strength and ductility is compromised. These films are of very thickness in the range of 10 to 30 angstrom, and sometimes the inherent nature of the process during the compaction helps in elimination or reducing these porous impurities. How? The relative movement between the powder particles during the compaction helps to break the surface impurities and improve the metal to metal contact. Okay. And the alternatively, reducing environment or vacuum also help in facilitating the good metal to metal contact for sintering purpose. Then surface area to volume ratio is another important characteristic of the powder particles, like the powder particles of the spherical shape, like say, so volume is given by pi by 4. So here if we see, let us start fresh. So if we see the surface area to the volume ratio of the powder particles for a spherical shape is found to be the minimum. Okay, the area to volume ratio is minimum for the spherical powder, while for the other shape powder particles, like if it is needle, the surface area to volume ratio is higher, and this ratio is found to be A by V ratio is found to be equal to the 6 for the spherical shape. But if we talk of the other needle shape or the flaky shape particles, then this A by V ratio is found to be more. Now, what happens when the A by V ratio is more? Like the surface area is more, so it will be more exposed to the environment in which it is getting exposed. So, the chances of the impurity formation at the surface, that will be more. Interparticle, so greater the surface area, now the contact between the powder particles at the surfaces will also be enhanced. So, if the surfaces are clean, then the diffusion across the interfaces, that will be enhanced. Okay. Another thing, if the powder particle is small, then the A by V ratio will be more as compared to the case of the large size powder particles for the same volume. Okay. So, it is always good to use the finer powder particle size because it offers the less higher A by V ratio, which in turn facilitates the improved metal to metal contact, increased metal to metal contact between the powder particles, facilitating the sintering and diffusion across the interfaces, and that in turn helps in development of the stronger components as compared to the case when we have the smaller A by V ratio. Okay. So, there are two aspects that are affecting the A by V ratio, one is the size and another is the shape. So, smaller size particles will be resulting in the greater A by V, that is 1 as compared to the coarse ones, and spherical shape particles will be resulting in the lesser A by V as compared to the needle and flaky particles. So, increase in the particle size reduces the A by V, as I have said. Spherical shape particles also produce the minimum A by V, it is 6, and for other shape particles like flaky and needle shape, it is greater than 6. And that is why if we have higher A by V ratio, whether it is being realized through the flaky or needle shaped particles or through the small size particles, it increases the surface interaction with the atmospheric conditions in which it is being processed, like say during the sintering or during the compaction, which in turn causes the agglomeration. Agglomeration reduces the flowability. Okay. So, the greater A by ratio in general reduces the flowability. Okay. On the other hand, interparticle a higher A by ratio increases the interparticle surface area contact, and that in turn increases the interparticle bonding, which in turn helps in increasing the mechanical properties. Okay. So, it is always good actually to have the higher by V ratio for improved sintering, improved bonding and improved mechanical properties. Okay. Now, the flow characteristics and interparticle friction. Okay. So, obviously, the size, shape of the powder particles significantly affect the flow behavior. Okay. So, the relative motion between the powder particles depends on the interparticle friction, which in turn affects the flowability and packing behavior. Okay. So, how to check the interparticle friction? Okay. So, like let us say we have the powder particle hopper of the powder particle here. Okay. And this hopper is open. So, powder particle will be falling and it will be getting piled up like this. So, on free pile up, there will be heap of the powder particles. Depending upon the friction, it will pile up like this. So, the angle of the surface that is produced, this is known as angle of repose. Angle of repose. So, if the powder particle if the friction at the powder particle interfaces is high, angle of repose is high. If the friction between the powder particle is less, then the angle of repose will be less. Okay, so the angle of repose is used as a parameter to quantify the interparticle friction. If the interparticle friction is more, obviously flowability will be less. The voids and the gaps between the powder particles will be more, and that in turn will affect the packing behavior. Okay, so relative motion between the powder particles depends on the powder particle friction, which in turn affects the flowability and packing behavior. Angle of repose, as I have said, steepest angle of repose is the steepest angle at which material can be piled without collapsing. Okay, so higher is the angle, greater will be the interparticle friction. Large angle shows the higher friction between the powder particles. Okay, fine particles cause greater friction than the coarse ones. Okay, spherical particles will reduce the angle of repose because of the reduced interparticle friction, and the flowability is judged from the time required to fill the cavity. Okay, time required to fill the given amount of the powder particles of the mold cavity in a standard, using a standard orifice size. So, say our orifice size is fixed, and this is the cavity which is to be filled in by the powder particles. So, how much time it takes to fill the mold cavity of a given volume using the standard size orifice, that time is used as a measure of the flowability. If it takes longer time, means flowability is less. If it takes lesser time, flowability is good. Okay, the flowability is just from the time required to flow a given amount of the powder through a standard orifice size. Okay, now the packing factor is the another one. This is just in two ways. One is the true density, how good the packing is there of the powder particles. One is the true density, another is the apparent density or the bulk density. Both are used as the same interchangeably, apparent density or bulk density. So, if we take the material of a given volume V, when the material in form of ingots without any porosity, so its weight divided by volume gives us the true density, that is the normal density. But when we use the powders, okay, say there is a mold, okay, in the and the powder particles have been filled in this. So, obviously, there will be lots of porosity and voids between the powder particles. Okay, the volume is V. When the powder particles have been filled in a given volume, then we take the weight W. So, this small w by V, this gives us the density which is significantly lesser than the true density. Why? Because there are a lot of voids and gaps between the powder particles. So, this density will be termed as the powder particles which are filled in a given volume, and then the weight of the powder particles is used to quantify the bulk density or apparent density. Okay, and this apparent density is so our apparent density or bulk density is always lesser than the true density of the material due to the presence of the voids and porosity. That is very simple. So, the different characteristics of the powder affect the apparent density or bulk density, like the size or size range, shape, okay, and interparticle friction, smoothness. All these affect the presence of voids and the porosity between the powder particles, and that in turn will be affecting the apparent density. So, as I said, the packing behavior of the powders is judged in terms of the true parameters. One is true or bulk density, true and bulk density. True density is the density of the material in the solid ingot form, which is free from the pores and voids. But the bulk density, also known as the apparent density, is obtained using the weight and the volume of the loosely heaped powder particles. The bulk density depends on the porosity and the pores and voids between the powder particles. Therefore, bulk density is always lesser than the true density. Okay. Apparent density is the weight of the loosely heaped quantity of the metallic powders for filling a given volume of the mold cavity, and the powders of the lower apparent density need the longer compaction stroke, and the stroke length depends on the size range and surface roughness. Let me explain a little bit this. if we use the powder particles of the coarse size, then the gap between the powders will be large. So, in order to compact and reduce the porosity up to the desired level, what we need? We need the longer stroke of the piston for compaction. Okay, and if we use the large size range in the appropriate quantity with the smoother surface particles, then the voids and the gaps between the powder particles, that will be reduced significantly, and that in turn will help in increasing the apparent density, and therefore the stroke length, that depends on the kind of size range, shape and surface roughness of the powder particles. Packing factor, which indicates the ratio of apparent density to the true density. We know that apparent density is lesser than the true density, and therefore this packing factor is always less than 1. Okay. Usually it ranges from 0.5 to 0.7, which means if the apparent density is high, then the packing factor also will be high. So, the powder particles of the different sizes of size range increases the packing factor, because it minimizes the voids and the pores between the powder particles, especially in case of the large powder particles which are filled with the fine powder particles. And when the compaction is done, the gaps and voids and the porosity between the powder particles will be reducing. So, packing factor increases during the compaction because of reduction in these voids and pores. And so, packing factor increases through the during the compaction through the rearrangement and deformation of the powder particles. And if we continue to do the compaction, then eventually all porosity and voids will be eliminated, and our packing factor will become equal to the true density. Porosity in powder metallurgy is defined as a ratio of the volume of the voids or pores between the powder particles and the bulk volume. Okay, I have already explained this. So, the porosity percentage, say it is P, and so and the packing factor say is PF. Okay, so the porosity percentage plus packing factor percentage. Okay, PF. So, this sum of this will be equal to 1. Greater the porosity, lesser will be the packing factor. If the porosity is reduced, packing factor will be enhanced, and that is why algebraic sum of the porosity and packing factor is found equal to 1. Now, I will summarize this presentation. In this presentation, basically I have talked about the various characteristics which are very important for manufacturing the components using the powder metallurgy approach. So, it is important that powder particles of the desired characteristics is selected, so that the sound and good quality product using the powder metallurgy can be prepared. Thank you for your attention.